what we discussed last time in 11.6, which was, you remember the topics we discussed? We discussed about directional derivative. What else have we discussed about? I'm going to split the fields, although they are related, gradient and the steepest ascent and descent. So in which direction will z equals f of x and y differentiable function, and when the derivative is continuous, will this have the maximum rate of change? This is just review. Why am I doing review? Well, after talking to you on a personal basis, like one-on-one basis by email and a little bit in person, I realized that you like very much when I review. When I briefly review some of the notions, I will give you the essentials for the section. That was 11.5 is embedded in this, embedded. So 11.5 is embedded in 11.6, and in one shot we kill both of them. In 11.7 you're going to see some extrema of functions of two variables like max and min, and then we have 11.8, which is Lagrange multipliers. What have we done about this differentiable function with continuous partial derivatives? Let's assume it is smooth. Okay, and in that case, we define the partial, the directional derivative in the direction of u being a unit vector at the point xy, but let's fix it x0, y0, using a limit of a difference quotient, just like any derivative should be introduced. But I'm not going to repeat that definition. Why is that? Because I want you to give me an alternative definition, which is something that is simpler to use in applications, which is what? Who remembers? The partial derivative of f with respect to x measured at the point x0, y0 I'm going to use this color, and then I'll change the color, and I'll say times u1 plus, change the color again, f sub y at x0, y0 times u2. And this times is just the times multiplication between real values, because u1 and u2 will be nobody but the components, the real value components of the unit vector direction that we have. So guys, remember, direction in this book means unit vector. Every time I say direction, I should say that's a unit vector. Is there any other way to express this? Maybe with a vector multiplication of some sort, multiplication between vectors. See, what if I had a pink vector with pink components and a blue vector with blue components? I'm getting somewhere, and I'm sneaky. And you know where I'm getting, because you've had chapter 9 fresh in your mind and a certain product between vectors. So what is this? It's a dot product. Excellent. Rachel, right? So it's a dot product. And I'm going to write it, and it's going to be just the gradient of f at the point P0. But I'm going to write it again x0, y0, although it drives me crazy to have to write that all the time. Dot product or scalar product with what vector u? I'm not going to put a bar on that because that would be like an oxymoron. The gradient is a bar thing. It's always a vector, so I'm not going to write a bar, but I write a bar on u, reminding you that u is a free vector. All right, do you like this? Yes, it's a compactified form of the fluffy expression we had before. It's much easier to remember than the limit definition, of course, it's equivalent to it. And in applications, we ask about that all the time. What was the gradient? So see, in mathematics, everything is related, and talking about, speaking about the devil, I mean, not you, but we weren't talking about you. Just this gradient f at the point P will simply be the vector whose components in the direction of I and j are the partials. The partial derivative with respect to x plus the partial derivative with respect to y. Okay, last time we dealt even with gradients of functions of more variables. If I have n variables, x1, x2, x3, xn, then this vector will have n components. F sub x1, f sub x2, f sub x3, f sub x4, somebody stop me, f sub xn. So I have n of them, and it's an n-uple. It's a some ordered sequence, let's go an n-uple. Okay, a set of n elements in this order. It's an ordered set in Rn. All right, so the order matters. Now, steepest ascent and descent, in which direction do I have the maximum rate of change? And the answer is, this is Q and this is A. The maximum rate of change happens in the direction of the gradient at every point of the domain where I have smoothness, or C infinity, or C1, whatever. All right, and what else? I claimed last time, but I didn't prove, that in that direction that I claimed, C from claim, the directional derivative is maximized exactly in the direction of the gradient. Can we prove that? Now we can prove it. Before I couldn't prove it because you couldn't see it, because I didn't look at it as a dot product, and we were all blind, like guiding each other in the dark, me a blind, you blind, we couldn't see. Now we can see. So now we can see how to prove my claim that the directional derivative, which is measuring the maximum, is measuring the instantaneous rate of change in a direction, compass direction, like, what is that, east, northeast, south, west, whatever. Those are the compass directions, like I plus j over square root 2, and so on. Those are called compass directions because you hold the compass in your hand as horizontal as you can, and you refer to the floor. Even if you are on a slope, maybe you imagine me on a slope hiking or whatever, going down, going up, but the compass should always be kept horizontal. Do you hike, Alex? I'm sorry, I'm going to put you on the spot. So, whatever you do when you take a path up or down is measured in the direction of the horizontal plane, the compass direction. And that is the gradient I was talking about. You see, it's a function, is a vector in plane. That means a geographic compass direction. Prove it. Let's prove the claim. Let's prove the claim because it's Tuesday and it's almost weekend and we have to prove something this weekend, right? Now, do you like what you see? Well, I have no idea. What if I want to measure this? This could be a negative number, but it doesn't matter. Assume that I take the dot product and I think, well, it's a scalar product, it must be positive. What do I get? This guy, if I'm a physicist, I'm going to say this guy is the length of the first vector at P0, gradient at P0, times the length of u, that is 1. Last time I checked, u was unitary, so that's silly of me, but I'll write it anyway. Times the cosine of the angle between, cosine of the parenthesis, angle between nabla f and u. Okay, when is this maximized?
When the angle between nabla f and u is 0.
When, exactly, when this is pi, so this quantity is maximized. Gosh, I hate writing a lot. I had to submit homework in the past 2 days, and one was about biological research and the other one about stress management. The stress management class stresses me out the most. I shouldn't make it public. Really, because we have to write these essays of 7 or 8 pages every Tuesday, every end of the week, twice a week. So I realized how much I hate writing down a lot. And what a blessing it is to be a mathematician. You abbreviate everything, you compress everything. I love formulas. So what we have here is maximized when the cosine is 1. And if you have it from 0 to 2 pi open, then theta 0 is your only option. Well, if you take it in absolute value, you could also have it in the other direction, cosine pi, but in that case you change the sign. So what you get a maximum, let's say you hike, right? I'm just hiking in my brain. The maximum rate of change in this direction, climbing towards the peak. And then the steepest descent is the exactly minus gradient direction. So I could have 0 or pi for the angle. That's the philosophical meaning of that. All right, so the directional derivative, which is this guy, when does it become maximum? When the angle is 0. So I'm done, QED. What does it mean? That I know this happens when direction u is the direction of the gradient. Can I write it u equals gradient of f? Not quite. I should say divided by norm or magnitude. Why is that? Then you say, Magdalena, didn't you say like 10 times that u is a unit vector? You want u to be a unit vector direction, so the direction should be the direction of the gradient in order to maximize this directional derivative. But then you have to take the gradient and divide it by its magnitude. Let's compute it. Let's see what we get. Let's see what we get. Now, I'm sorry about my beautiful handwriting, but I'm going to have to, I have room here. And actually, I can use this formula. So, in the direction of the gradient, when u is the gradient, let's take u to be, what did I say over there? Gradient of f over the magnitude of gradient of f. I'll take this guy and drag him here, substitute him here. What will the value of the directional derivative be? We've done last time the same thing on an example. We've done it on a function, beautiful, f of xy equals x squared plus y squared. This is the type of function I like because they are the fastest to deal with. But anyway, we'll have all sorts of other functions. What am I going to write here? I have to write, well, by definition now, by my new way to look at the definition, I'm going to have a gradient at a point. It's a vector. Dot, who is u again? The gradient this time, that special value, divided by absolute, by magnitude of the gradient. But what in the world is that? This animal is, what if you take a vector multiplied by itself? Dot product, look, dot product. What you get is the magnitude squared. All right, so I'll go, the pinky guy and the pinky guy are magnitude of f squared divided by magnitude of f. And Alex said, but wait, that's just, I know, I didn't want to just jump ahead too fast. We get gradient of f in magnitude. So, beautiful. So we know who that maximum is. The maximum of the rate of change will be for z equals f of xy, the max of the rate of change is, what is that again? Magnitude of nabla f in the direction nabla f divided by its magnitude. This is what we discovered. And now I'm going to ask you, what is the minimum rate of change at the same point?
Just parallel, or
Just parallel opposite.
Yeah.
So it's I'm gonna have the so-called highest, steepest, not highest, highest means maximum, the lowest value. So I'm gonna have the lowest value, which indicates the steepest descent, me going down in the snow, I'm dreaming on a sleigh or on a plastic bag. That will give me the steepest descent, and the steepest descent will correspond to what? I'm going to make an NB, nota bene, in Latin. Note, the minimum will be minus magnitude of f, nabla f, in the direction, in the opposite direction. Shall I write it in words? Let me write it in words. OPP from opposite, no, from opposite direction. What do I mean opposite direction? Opposite direction to the gradient, which is the same direction if you think about it, because it's the same line. So it's going to be minus nabla f over magnitude of nabla f. It's like when we were on our hill, which was 1 minus x squared minus y squared, whatever it was. We had I plus j for the descent, and minus I minus j for the ascent, the steepest descent and the steepest ascent. We've started with the examples because it's easier to understand mathematics. Actually, it's easier to understand anything on an example. And then, if the example is good, if the example is bad, it's confusing. But if the example is good, you understand just about any concept, and then you move on to the theory, and this is the theory. And it looks very abstract. When somebody steps in this classroom and they haven't taken more than Calc 2, they will get scared. They will never want to take Calc 3. Well, that's why I didn't want to scare you off yet. Okay, so this is what you have to remember from section 11.6 with 11.5 embedded in it. Now, one thing that I would like to see would be more examples and connections to other topics. So one example that I picked, and I think it's a nice one, I just copied from the book. I usually don't bring cheat sheets. I don't like professors who bring books to the class and start reading out of the book. I think that's ridiculous. I mean, as if you guys couldn't read your own book at home. And I try to make up examples that are easier than the ones from the book to start with. But here's example 4, which is not so easy to deal with, but it's not hard either. And I picked it because I saw this browsing to the previous finals. I saw it as a pattern coming every now and then. Find the direction in which f increases or decreases most rapidly. I have to write down beautifully. Find the direction in which f increases or decreases most rapidly at P0 coordinates 2, 1. And what is the maximum, that's a question, what is the maximum rate of change or of increase? This type of problem is also covered in the Khan Academy videos and also the MIT library, but I don't feel they do a very good job. They cover it just lightly as if they were afraid to speak too much about, give too many examples and talk too much about the subject. So what do you guys want to do with this one? Help me solve the problem. That was kind of the idea. So we start with computing the what? The animal called, what's the animal gradient. Thank you very much. So we do that, and we start differentiating. With respect to x, we get a product rule. So you have product rule and chain rule. You have 1 is differentiated times e to the 2y minus x, the way it is, plus x undifferentiated. The second guy, prime, copy and paste Magdalena, times, don't forget the minus 1, because I'm talking to myself. Because if you do, you get a 0 on this in the final. I'm talking to myself, okay? All right, plus, parentheses, the same procedure with respect to y. When I do it with respect to y, this is a good review of the whole chapter. Yes, sir?
Can we do the derivative of e raised to power 2y minus x? You don't write 2y minus x again. Like the derivative of e raised to power 2x is 2.
This prime with respect to x. Am I doing something wrong? No. Are you with me? So this guy, prime with respect to x, I'm going to write it. Yes, copied, and take that argument and differentiate with respect to x. So I did it right. Right? Okay. The second one, x is a constant for me right now. Who is the variable? Y. So I copy and paste e to the whole argument times, I cover everything else with my hands, and I differentiate the argument with respect to y. And I get times a 2 and a j, and I say, thank God, this was a little bit long. You realize that if you make the slightest algebra mistake, it's all over for you. In that case, I asked my colleagues, what do you guys do in such a guy missed that or missed this? 0. 0. No question. Okay. Maybe a little bit, maybe time a little extra credit. But pay attention to your algebra. So, you know what you need to do. Now I'm going to go on and say, but I am at the point 0. By the way, I really don't like it, what we did in the book. Okay, I should not say that out loud, but it's too late. The book denotes that sometimes, well, we try not to do that too often, but nabla f sub 0, because some other books use that. I don't like that. So every time, you should never do that, because it gives the feeling that you are differentiating a constant or something. Oh, I don't know. So I'll always try to say gradient at P0, which means I have a fixed value, but I don't fix the value before I do the gradient. This is too confusing as a notation. Don't do it. Close your eyes when you get to it, when you read it in the book. Okay. Now, I have to plug in, instead of x a 2, I try to remember that, and y equals 1. So I go 1 times e to the 2 times 1 minus 2 plus 2 times e to the 2 times 1 minus... I wish I had data with me. I mean, the guy from Star Trek. Because he could do this in just a fraction of a second without me having to bother with this whole thing. Okay.
But then if data existed, why would we be mapping?
Exactly. So we do this so that we can program people, I mean androids, and eventually learn how to clone ourselves. Okay. So let's see what we have. E to the 0 is 1. E to the 0 is 1. 1 minus 2. Are you guys with me? I'm going too fast?
No, the point is y component is equal to 1, x component is equal to 2.
X component equals to 2.
So
X0 is 2 and Y0 is 1. And
2
I
multiplied 1.
plug in X0 equals 1. So 2 times e to the 2 times 1 minus 2. You think I like it? I don't like it. But anyway, it's my life. I have to go on. So we have 1 minus 2 was minus 1, right? Minus 1i. Minus 1i sounds scary. Okay. Plus 4j. Minus I plus 4j. Is it lovely? No, I hate it. The magnitude is going to be square root of 17. But that's life. I mean, you as an engineering majors see that all the time, and even worse than that. So I'm going to say the gradient of f at P0 in magnitude will be square root of 17. What is that? That is the maximum rate of change, right, guys? But in which direction does that happen? And the book, my beloved book, says in the direction of minus I plus 4j. That's our answer. Say in the direction of...
Over root 17.
No.
Oh.
Let me tell you what. We thought about that as authors when we wrote the book. So I said, if you say in the direction of, then you have to say over root 17. And my co-author said, no, actually, Magdalena, is a matter of English. Since you're not a native, you don't understand.
Oh.
In the direction of a certain vector means like this, the direction of a certain vector, the direction could be that. But if I could say equivalently in the direction double dot minus I plus 4j over square root of 17, meaning that this is the direction. It's a matter of interpretation. I don't understand it, but it's your language.
In this sense, what should we write? Like the answer. I'm saying...
Which one you are?
Which one do I like? This.
Awesome. That would keep to that.
Thank you. So if we define direction to be a unit vector, let's be consistent and not say of me, of you, of my cousin, of who knows. All right. Was this hard? No. Do I have a caveat about this kind of problem? Yeah, that was kind of the idea. If I put that in the midterm, guys, please do it 2 or 3 times. Make sure you didn't make any algebra mistake, because if you know the theory, I will still give you like 30% or something, but if you mess up with the algebra, I have no choice but giving up the 70%, whatever that is of that. I try to be fair and give you something for everything you do and know, but try not to mess it up too badly. It's very easy to mess it up. Yes, sir.
So which way is increasing?
Okay, find the direction in which f increases or decreases most rapidly. Okay, the direction in which I could draw it, this is increasing in the direction of that. At what rate? At the rate of square root of 17. Good question. How about the other one? In the direction of plus I minus 4j over square root of 17, I get the rate of change minus square root of 17. And that's it. Do we have to say that? I give you extra credit if you say that. But at this point, I'm saying I'm happy with what we just wrote on the board.
Basically, the most rate of the change minus the
So so it's like finding on which path are you gonna get to the top the fastest. When you climb a mountain, it's the same kind of question, because it's all about z being an altitude. Z equals f of x. I will go ahead and erase the whole thing, and I wish you good luck. Now I wish you good luck because I was asked by Nitish to solve a problem like the one you gave me in the web board, but I don't remember it, but it's okay. It was a review of what we did last time, and we said instead of that, where the tangent plane, we know what that is, at P0 was, guys, by the final, I want this memorized, there is no question. So Z minus Z0 is like Taylor's formula in the linear approximation. You truncate, you throw away the second order, and so on. So what is that? F sub x at delta x, x0, y0, I'm lazy, times x minus x0, this is the delta x, this is the delta z. And this is not the round surface, curvy and everything. This is the plane approximation, the planar approximation, APPR. I'm not done. Plus f sub y minus y. So this is the equation of the plane that's tangent pi at P0. And let me draw the surface pink, because I'm a girl, and because I want to draw this in pink. Let's call it some S from surface. Can you paint an S here? Okay. But if I'm giving the same picture but a different equation, so I have f of xyz equals constant, that's the implicit form. I make this face. Why do I make this face? Because I got 3 confessions. I'm more like a priest in priestess in mathematics. People don't like implicit differentiation. We will do a little bit of that today because you told me your stories from implicit differentiation, and I got scared. Those are horror stories, and I don't want those to repeat in the final or the midterm. So I'm going to do something with implicit differentiation as well. What did I want to say? If we apply this, would be wrong. But we have to remember what the normal will be. And the normal was the gradient of big F. So those will be f sub xi plus f sub yj plus big F sub zk. And for such a surface given implicitly, the tangent plane looks a little bit differently, but it's the same story, and I proved that. You may not believe it or may not remember, but I proved that it's the one and the same thing. So I get f sub x at 0 I0. This was the A guy, right? Times x minus x plus. What's next? from the coefficients coming from the gradient. That was the gradient. So this is f of x, y, z equals c. And the gradient was, this is the normal. F sub x, F sub y, F sub z, angular bracket equals gradient of f, which is more or less the normal. The normal, unit normal will be just gradient of f over length of f. So let's continue. F sub y at x0, y0 times delta y. This is b. I had a problem with memorizing these, especially since when I was 18, I did not understand them whatsoever. First year of college, I had to use markers, put them in markers, and glue them to my closet. Because when I was 18, of course, I was looking in the mirror all the time. So whenever I got into the closet, opened the door, this is the mirror. Next to the mirror, there was this formula. So whether I liked it or not, I didn't. I memorized it just by seeing it every day when I opened the door. Yes, sir?
Last green one, should that be x minus x or z minus?
Z minus 0, that is minus 0. Thank you. So again, you have delta x, delta y, delta z. Thank you. Is it hard to memorize? No, not if you put it in markers. I think it will be just fine. What have we done last time? Let me review it really quickly. We said, wait a minute, how come they are one and the same? You said, oh, I'm getting a headache. I don't understand why they are one and the same. And we said, yes, but you see, this guy is nothing but z minus f of xy. So from this form, you can make it implicit by pulling out f to the left and creating this big f of x, x, and y, and z equals z. And what does it mean? It means that f sub x will be, oh my God, this has nothing to do with us, minus f sub x. F sub y will be minus f sub y. Am I right? And f sub z, big F sub z is simply, there is no z here, 1. So, coming back to the guy's ABC, forget about ABC, I'll take the A, and I'll replace it with minus f sub x, which doesn't write, and it's time to use, okay, to go away, minus f sub x, and this is f sub y, with a minus. And finally, Mr. C, who is happy, he is 1. So he says, I'm happy. You are going to separate me. We are going to separate him. So this equation is nothing but what? Let's write it from the left to the right. Let's keep the green guy in the left-hand side. And everybody else goes for a moving sail. The blue and the pink go away. And when they go to the other side, they have a minus. Pick up a minus sign. But with a minus here is a plus sign. Are you guys with me? So the blue guy has moved and changed sign. Where's the pink guy? The pink guy will also move. And he picked up this one. So practically, this and that formula are one and the same. They are both used for the same tangent plane. It depends how you introduce the tangent plane. And Nitish, before class started, it was 20 or 25 minutes before class, when I was in a hurry, I answered you briefly. You made some algebra mistake in the, you got it. I would like to make up one like those, but I forgot what your surface was. Was it an ellipsoid? Okay, I'll make up an ellipsoid. Yeah. If you have it with you. If you don't have it with you, that's fine. So I'm going to go ahead and keep just the implicit equation because the ellipsoid is given by the implicit equation. And everything else I will erase. And that was problem 24. How many problems? Well, you still have a lot, up to 49, 42. Okay, I reduced it. Now, when I sent you an email on Sunday, I said I am giving you an extension. I was giving you an extension. And till a lot of March, because I thought March the 2nd, and I gave a few more days, so you have one more week.
Spring break.
Spring break's the 14th, but this is due on the 9th, right?
The 10th.
The 10th, the 9th, 10th, maybe I don't remember. So, Nitish, what was your problem? What's your problem? What?
3x squared.
Can I take it?
30 questions.
So you have an ellipsoid, which comes from the ellipse 3x squared, well, x squared. Then you have a 2z squared of 9. And it says, you look at the point P of coordinates minus 1. I haven't even checked if it's correct, but it should be. So 3 plus, I did not program the problem. 3 plus 4, 7 plus 2, 9. So he did a good job. We want the tangent plane. I'll put it here. We want the tangent plane. How do we compute the tangent plane? We say this is f of x, y, z, right? So f sub x equals 6x, f sub y equals 2y, f sub z equals 4z. Computing it at p0, what do we have? X is minus 1, y is minus 2, z is minus 1. I should get negative 6, negative 4, and minus 4. Right? And then I should plug in and get minus 6 times x minus minus 1. I have to pay attention myself. It's not easy to get the algebra right. Minus 4 times y plus 2 minus 4 times z plus 1 equals 0. And I hope I get what you got, minus 6x minus 4y minus 4z. So many of those. I'm going to divide by 2. I'm not getting that. And then minus 6. I'm going to write it down. So it's even, right? The whole thing minus 18. Divide by 2. Should be, and divide by 2, and did you change the signs, Nitish? Oops. What's your password? Okay, then. Check if I'm getting the same thing you got. So I get 3x plus 2y plus 2z. I divide by minus 2, right? Plus 9. Did you both got the same thing?
I didn't divide by 2.
You didn't? Well, I'm trying to simplify all my answers. And this is the simplification. So I guess, of course, that you enter it like that is going to work. Now, I need you guys to help me on this one. Find the parametric form. It's so easy, but this is a problem session. So, of the line passing through the same point that's perpendicular to the tangent plane. Express your answer in the form, parametric form of the type, the one that you know that I don't like very much, but I will write it down. A2t into B2, A3t plus B3. This is how he wants me to write it, which I don't like. I would have preferred it to be in symmetric form. It's the same. I'll put a t and I'm fine. So x minus x0 over L, y minus y0 over M, z minus z0 over N. That was the symmetric form. I make it parametric by saying equal to t. So what were the parametric equations? X equals LT plus X0, that's the normal. Y equals MT plus Y0, Z equals NT plus Z0. So finally my answer, I'll check with Nikish's answer in a second, should be, take the normal from the tangent plane 3 to 2, right? 2t plus whatever, this is 2t plus z equals, first is 3. 3 to 2. 3 to 2 plus x0, y0, z0. So erase the pluses and put minuses. And those should be the equations. And I should write them down. It's out. It's okay. You have the same. Now you just have to take them, this, and that, and put it in this form. This is a combination problem. Why do I say combination problem? It's combining chapter 11 with chapter 9. This was the review from chapter 9. Did you have trouble understanding the gradient or the tangent planes or anything like that? Implicit form, explicit form. Let me do an application. So I'm doing review anyway. I'm done with the section 11.6, but before I want to go further, I want to do some review of chapter 11, sections 11.1 to 11.6. I said something about implicit differentiation being a headache for many of you. One person asked me, how do you compute z sub x and or z sub y based on the equation x squared plus y squared plus z squared equals 5. And of course, this is implicit differentiation. Why implicit? Okay. Because this is an implicit equation of the type f of x, y, z equals constant. When do we call it explicit? When one of the variables, x or y or z, is given explicitly in terms of the other two. So if this would be, well, here it's hard to pull it out, but what would it be? Upper part, then lower hemisphere, z would be plus or minus, so you have two caps, two hemispheres, plus minus, square root 5 minus x squared minus y squared. Well, that's two functions. We don't like that. We want to be able to do everything in one shot without splitting it into two different graphs. So, how do we view z to be a function of x? You're going to ask yourself. You imagine inside this thing that x and y are independent variables. Independent variables. They can take whatever they want. One is temperature, one is time. They run like crazies. But z depends on both temperature and time, like us, unfortunately. It's so cold outside. I hate it. Okay. You promised me, well, you promised me and it came true. Who promised me? Matthew. Give you a brownie point for that because you said last week it's going to be 80 degrees. And it was. So the prophecy came true. On the other hand, it came back to bad. So, and of course, it's not Matthew's fault. He didn't say what's going to happen this week. All right. In this case, implicit differentiation is just a philosophical thing. It's a very important philosophical step that you are taking. Think. Think of z being a function of x and y. And 2, differentiate z with respect to x. So what do you mean differentiate z with respect to x? By differentiating the entire equation, both sides of an equation with respect to x. So for you, x is the wanted variable, y is like a constant, z is a function of x, it's not hard at all. Okay, so what is going to happen actually if you were to do it? Theoretically, you would go like that. If I'm going to differentiate this guy with respect to x, what is the philosophy? The chain rule tells me differentiate f with respect to the first variable, right? And then times dx dx. And you say, God, that Magdalena, that was silly, right? Differentiate with respect to x. That's the chain rule. Plus, differentiate f with respect to the second variable. And then say dy with respect to x. But are dx and dy married? Do they depend on one another? Do they file an income tax return together? They don't want to have anything to do with one another. Thank God. So x and y are independent variables. If you are taking statistics or research in any other kind of physics, chemistry, you know that these are called independent variables and this is called the dependent variable. And then you have what's called a constraint. In physics and engineering, in mechanics, f of some three variables equals c is called constraint usually. Okay. So this guy is all silly. These guys don't want to have to do anything with one another. And then you get plus, finally, df with respect to the third place. And then that third place, z, is occupied by a function that's a function of x. So you go dz dx. Why del and not d? Because poor z is a function of two variables, x and y. So you cannot say dz dx. You have to say del z dx equals u. Thank God, I got to the end where I wanted to get. Now, if I want to see what's going on, this is a piece of cake, that's 1. And I get that Mr. z sub x, which other people write dz dx, but I don't because I don't like it. I keep mixing x and z, okay? Equals, how do I pull this guy out? How do I substitute for that? Get Mr. first fellow here. To the other side, he's going to pick up a minus. At whatever p I have. Divided by, so this guy, divided by this guy.
What happens to df, dy, dydx?
So again, that is a very good thing. So df dy was behaving, he was nice. But when we got to dy with respect to dx, y said, I'm not married to dx. I have nothing to do with dx. I'm independent from this. So dy dx is 0. And so this guy disappears. dx is 1. Duh, that's a piece, okay? So I'm done. This is actually a formula that looks sort of easy, but there is a lot hidden behind it. This is the implicit function theorem, where you, of course, assume that these partial derivatives exist, are continuous, everything is nice. It's a beautiful result. People actually get to learn it only when they are big. I mean big, mathematically mature in graduate school. first or second year of graduate school. We call that intermediate analysis or advanced, very advanced calculus, because this calculus is advanced enough, but I'm talking about graduate level calculus. And this is the so-called implicit function theorem. So if you will ever be even not necessarily a graduate student in mathematics, but a graduate student in physics or something related to pure science, remember this result. So let me see what's going to happen in practice. In practice, do we have to learn this? No. In practice, we can build everything from scratch. Again, just like the way we did it with the formula. So for the example I gave you, should be a piece of cake to do the differentiation. But I'm going to step by step. Step one, think. You have to think. If you don't think, you cannot do math. So you have x squared plus y squared, the independent guys, and z, who is married to both of them. Or maybe z is the baby. These are two spouses that are independent from one another. And z is their baby because he depends on both of them. So you thought you have a different approach to the problem, different vision of what's going on. Now finally, step two, differentiate with respect to one only, x only. You could, of course, do the same process with respect to y. And in some of the final exam problems, we are asking compute z sub x and z sub y. The secret is that, maybe I shouldn't talk too much again, is that when I grade those finals, if you did z sub x, I give you 100% because z sub y is the same. So I really don't care. Sometimes there are so many things to do that all I care is, did he or she cover the essential work? So, with respect to x, x squared divided, well, differentiate with respect to x. Good, first step. Now, y squared differentiated with respect to x. 0. Am I going to write 0? Yes, because I'm silly, but I don't have to, right? 2 times z of xy. 2 jumps down, z of xy. I'm not done with the chain rule. Z of x. Very good. This is dz dx. I'm not going to write it completely like that, but it's the same thing. 5 prime is 0. Thank God. So you see, if I were to keep in mind that that's the derivative of big F with respect to x, I could plug in everything in here. I could plug in the formula. But why memorize the formula and plug it in when you can do everything from scratch all over again? Math is not about memorization. If you are good, for example, some people here, I'm not going to name them, are in sciences that involve a lot of memorization. More power to them. I was not very good at that. So I'm going to go ahead and write z sub x pulled out. Minus 2x divided by 2z. I'm too lazy to remind you that z is the baby and he depends on his parents, x and y. I'm not going to write that. And that's the answer. So you have minus x over z. So how, for example, how would I compute, if somebody says compute z sub x at the point on the sphere, that is 0, with 5, and 0, what do you have to do? You have to say z sub x equals, and now I'm asking you something that's tricky, minus 0 over 0. Assuming that the expressions, the derivatives are defined And the denominator one is different from 0. So whenever you do the implicit function theorem, you can apply it with the condition that you are away from points where derivative of f with respect to z are 0. So this is a problem that's not well posed. So to give you a well posed problem, what do I need to do on the final? I have to say, let's say, 2, 1, and 0.
Z can't be 0.
No, I know. So I go 0 is too easy. Let's have
2,
y
0,
to
1.
be 0. Very good. X equals 2, y is equals 1. Excellent. So z sub x at the point 2, 0, 1 will be, by the implicit function theorem, minus 2 over 1 equals negative. You see, that's a slope in a certain direction if you were to look at z with respect to x in the plane xz. Okay, what else? Nothing. There was review of chain rule and stuff. You have to review chain rule. Make yourself a note. Before the midterm, I have to memorize the chain rule. Yes, sir.
Can you go over linear approximation and calculus?
I will do that in either in the review session today or in the review for the midterm. Okay? And I'm thinking about that. In March, I want to dedicate at least 10 days for the review for the midterm. Yes, sir.
When is the midterm?
The midterm is on the 2nd of April. Okay? Several people asked me, okay, I forgot about that, I have to tell you guys. Several people asked me questions by email about the midterm. So the midterm, write down for yourselves, the midterm will be over the following chapters. Chapter 10. No, chapter 9. Chapter 9 is the review. Chapter 11. All. Chapter 10 only 10 what we have required. 10 1, 10 2, and 10 4. And chapter 12 all but section 4.6. Because I see that some of you study ahead of time. More power to you. You know what to read. Skip section 12.6, and I'm planning to not give you anything after chapter 13 on the midterm, but of course chapter 13 will be on the final, emphasizing at least 6 problems out of the 15 problems you have in the final. Okay, all right, we still have plenty of time. Chapter 9, guys, you were concerned about it. It's some sort of embedded, you see, wherever you go, wherever you turn, you bump into some parametric equations of a line normal to a tangent plane. That's the dot product that you dealt with, delta f dot n. So it's like an obsession, repetitive review of chapter 9 at every step. Vector spaces are very important. Vectors in general are very important. I'm going to move on to 11.7 right now. I'll take a break, and why don't we take a short break now, 5 minutes, and then we have to go on until 2:50. So practically we have 1 more hour. Take a break, eat, drink something. I don't want a big break, because in a big break we'll just fall asleep. I am tired as well, so we have to keep going.
Yeah.
Yeah.
I literally just sat there and I was like, no, I was sitting over and I was like, I refuse to leave this room. If Taylor comes and yells at me, I won't leave you until my giant leg already shows up at my door.
Yeah, I was walking back and there were probably people that were sitting out. I'm like, no. Just went down to her.
And then now I'm sure like the fire at Sam's West, I'm like, the fire at Sam's
Yeah, I'm sounding
We're
supposed to have fire drill that day at West.
Yeah.
Hey, Andre.
My roommate comes in. He's like, I was in there. Huh? There was a fire drill. I was like, nah. And he started screaming. Everyone got real scared, so I just went to my room. And we look outside. It's like, why not?
When is it supposed to open back?
I'm just like, I
I
did enough.
after
After
like
spring
the
break.
first after spring break.
That's the worst thing.
Sanford,
What about it?
there was a fire.
Partially burned down, and they had to throw away all the food, and it won't be open for like 2 weeks.
Wait, Sam's West?
Yeah. What you had to say was not
On the same place where it burns down, and you feel our pain.
Well, that would also mean that my building kind of burns down, so that would be pretty shitty.
I hope your room catches fire.
No, there's so much crap in there, like that sucks so much.
Lots of flammables.
That fish was in there.
Again, if it's just I
That'd be awesome.
That would be awesome. Alright, goodbye.
You ever seen that cat that runs around?
Yeah, the campus cat. One time it was on the roof of Sam's and some old lady was trying to get it down.
Last night it was like 15 degrees. She was like floating in front of the
Teaching us about literally professionals there.
I got another one. He's a nice one that talks about it. Or can the.
Well, all right.
I don't want to get for spring break.
You know, not the cross property.
Just talking about the status.
We made the something of the matrix.
I'm really
Yeah, it's hard to fix.
Okay.
But it says.
Well, just take it
I remember I had to do it, so I realized I'm pretty sure that's why I did it.
So did you try to
You're not
Yeah, I just,
Yeah,
I
so
something that you were
that's gonna be 1 over 2, 1 over 2.
That's what I.
You know why, right? Because 2, 2 is collinear to 1, 1, which is not unitary. And so when you unitarize this,
Oh, okay.
so the direction corresponding to 1 is exactly that.
Okay, that's what I didn't understand. Okay, thank you.
Where's your?
I don't know everything about
Good, you can go whenever you want. Even now. All right, I will start with a little bit of a review of some friend of yours. Since we are in Texas, of course, this counts as an obsession. This is going to be Extrema, functions of several variables. Do I draw better lately? I think I do. That's why I stopped drinking coffee and drinking white tea. That's good for you. All right, white tea. For some reason, the black tea was giving me the shit, you know, that too much black tea. I don't know, maybe it has less caffeine. Jasmine is good, green, white.
Green is better.
Okay, so about this saddle as a function of two variables, you know a lot already, but I'm asking you to compute the partial derivatives and the gradient. And you're going to jump on it and say, I'm doing review anyway, so we got 2x, and this is minus 2y. If I were to ask you the differential on the final or midterm, you would say that's f sub x dx plus f sub y dy. Everybody knows that. Don't break my heart. Don't say 2x minus 2y, because I'll never recover. Every time I see that, I die 100 deaths. So don't forget about dx and dy, which are the important guys called infinitesimal elements. This is a one form. In mathematics, any combination of a dx and dy, linear combination, is a one form. It's a consecrated terminology. But I'm not asking you about the differential, I'll ask you about the gradient. Alrighty, and that is a f sub xi plus f sub yj, which is exactly 2xi minus 2yj. And you say, all right, but I want to take a look. I always started with examples. Hopefully they are good. Let's look at the tangent vectors to the surface. We discussed about the notion of tangent vector before. Remember when we had r sub u and r sub v for the parameterization. Now look at the tangent vectors for this graph along the x direction going this way and along the y direction going this way. We see that both of them are horizontal at the origin. And that's a beautiful thing. And so this origin is a so-called critical point. Critical point for a differentiable function z equals f of xy is a point in plane x0, y0 where the partial derivatives vanish and according to the book, and many books all don't exist. Well, I don't like that. Even our book says if you have a function in Calc 1, let's say g equals g of u. Critical point. Remember what a critical point was? u0, in Calc 1 we said either a point where g prime of u was 0 or g prime of u0 doesn't exist. Although u is 0 is in the domain. I don't like that. You say, wait a minute, why don't you like that? I don't like that for many reasons. Practically, if you have the absolute value function, you'll say, yeah, but look, I consider the corner to be a point of non-differentiability, but it's still an extreme value, a critical point. According to our book in Calculus 1, yeah, we extended this definition to ugly points. Points where you don't have a peak or a valley or an inflection, but you have something ugly like a cusp, a corner, ugliness. I don't like that kind of ugliness because I want to have more information there. I may even have a point with a bigger problem than that. First of all, when I say critical point, I have to assume the point is in the domain of the function. But then what kind of ugliness I can have there, I don't even want to think about it. So in the context of my class, Calc 3 honors, I will denote And critical point is the x0, y0 such that f sub x at x0, y0 is 0, one slope is 0, the other slope is 0. F sub y at the x0, y0 equals 0. And no other ugly points. What am I going to call the any ugly points where derivatives don't exist? I simply say I have a singularity. I have a singularity. What type of singularity we can discuss in an advanced calculus setting. If you're math majors, you're going to have the chance to discuss that later on. So remember that I would prefer, both in the context of calculus 1 and calculus 3, to say critical value is where the derivative becomes 0. Not undefined plus minus infinity or something really crazy, one on the left, one on the right. So I don't want to have any kind of complications. Now, you may say, but I thought that since you have those slopes both 0, that means that the tangent plane at the point is horizontal. And that's exactly what it is. I agree with you. If somebody would draw the tangent plane to the surface S, S is from surface, but it's funny, S is also coming from saddle. So that's a saddle point, saddle surface. Origin is so-called saddle point, we don't know yet why. The tangent plane at 0, at the origin, will be z equals 0 in this case. Why? Well, it's easy to see. Z minus 0 equals f sub x, x minus x0 plus f sub y, y minus y0, but this is 0 and that's 0, so z equals 0. So thank you very much. Poor horse. I can take a horizontal plane, imaginary plane, and make it be tangent to the saddle in all directions at the point in the middle. Okay? All right.
So you're saying a critical point is where both
partial derivatives vanish. They have to both vanish. In case of calculus 1, of course, there is only one derivative that vanishes at that point. What if I were in, now you see, the more you ask me questions, the more I think, and it's a dangerous thing. What if I had z equals f of x1, x2, x3, xn? Critical point would be where all the partial derivatives will be 0, and then the situation becomes more complicated, but it's doable. Now there is a classification of special points. Classification of critical points. Based on second partial derivatives. The objects you want to study in this case are several. One of the most important ones is the so-called discriminant. What is the discriminant? You haven't talked about discriminant since a long time ago, and there is a relationship between discriminant in high school algebra and discriminant in calculus 3. The discriminant, the way we define it, is d or delta. Some people denote it by d, some people by delta. And that is the following. It's the determinant f sub xx, f sub xy, f sub yx, f sub yy, computed at the point p0, which is critical. So P0 first has to satisfy those two equations, and then I'm going to have to compute the D at that point. But you'll say, wait a minute, Magdalena, what the heck is this? Well, this is the second partial with respect to x, one after the other. Second partial with respect to y, one after the other. These guys are equal. Remember that there was a German mathematician whose name was Schwarz, the black cavalier, the black man. Schwarz means black in German. And he came up with this theorem that it doesn't matter in which order you differentiate, f sub xy or f sub yx is the same thing as long as the function is smooth. So I'm very happy about that. Now, there are these other guys, ABC. It's very easy to remember. It's from the song that you all learned in kindergarten. Once you know your ABC, you come back to the discriminant. So f sub xx at the point P0, f sub xy at the point P0, and f sub yy at the point P0. Second partial with respect to x, second partial with respect to x and y, mixed one, mixed derivative, and second partial with respect to y. You have to plug in the values for the P0 will be x0, y0, the critical point you got from what? From solving the system. So you got x0, y0 by solving that system. Come back, plug in, compute those, get ABC as numbers. And who is D going to be based on ABC? According to the diagram that I drew, it's easy for you guys to see that A and B and C are what? Related to D. So D will simply be A, B, B, and C computed at the point P0. So it's gonna be now that will remind you of something. AC minus B squared. Okay? When we had the quadratic formula in school, I'm gonna write it here. So what was the quadratic formula? ax squared plus bx plus c equals 0. That was algebra, baby algebra. What do we call that? High school algebra. x12 was minus b plus minus square root of b squared minus 4ac divided by 2a. Now, I don't know what kind of professors you had, but I had a teacher when I was in high school. Every time she taught me something and I did not absorb it, she was all over me. She was preparing me for some math competitions and she taught me a trick. She said, look, Magdalena, pay attention. If B would be an even number, take B to be 2B prime. Give me another letter. 2 big B. Right? Then the quadratic formula would be easier to use. Because in that case you get x12 equals minus b is 2b, so you have just 2b like that, plus minus square root 4b squared minus 4ac divided by 2a. She explained this to me once and then she expected me to remember it for the rest of my life. And then she said minus big B plus minus square root of big B squared minus AC. Do you see why? It's because you pull out the factor of 4. Square root of 4 is 2. 2 and 2 simplify. And then she gave me to solve problems.
What about the A?
What about the A?
Because you divide by
Divided by A. I forgot to write it down. So, because I didn't have space, I said I'm not going to bend and do more. So when you have x squared plus 2x, let's say minus 3. And she gave me that. And I said, okay, let me do it. x1, 2 minus 2 plus minus square root b squared minus 4ac, which is 12, divided by 2, and she started screaming. And she started screaming big time. Do you know why? She said, I just taught you the half formula. by half formula, she meant this one. So when I said, okay, the half formula. But then for maybe another 7 years, I did this with the formula that everybody knows. And at the end, I would remember I could have done the half formula, but I didn't do it because I'm in a routine. So the way she wanted me to do this was what? Who is the half of 2? 1. So put -1 plus minus square root of big B is 1 squared minus A times C, which is plus 3, divided by 1, divided by nobody. This way you don't have to simplify further, and you do it faster. So you get -1 plus minus root 4, which is -5 and 3. But of course, you could have done this by factoring. So you could have said, wait a minute, 2 numbers that multiplied, I didn't do it right. So it's 4.
It's supposed to be 2 and 1.
Yeah. So you get x plus 5 times.
It's x minus 1.
You forgot the
X
square root.
So what have I?
Square root of 4.
Square roots. I'm sorry, guys. Okay, thank you for that. 1 and minus 3. So x plus 3 times x minus 1, which is the exact same as x squared plus 2x minus 3 equals 0. All right? So just the way she insisted that I learned the half formula. I'm not insisting that you learn the half formula, God forbid. But see here, there is some more symmetry. The 4 doesn't appear anymore. B squared minus 4AC appeared here, but here it doesn't. Here you're going to have B squared minus AC. There is a reason. This comes from a discriminant just like that. And this is why I told you the whole secret about the half quadratic formula, not because I wanted you to know about it, but because I wanted you to see that there is a pattern here. You have, for the half formula, you have plus minus square root of a new type of discriminant. People even call this discriminant B squared minus 4AC, B squared minus AC. So for us, it is AC minus B squared. It's just the opposite of that discriminant you have here. Now, depending on the sign of this discriminant, you can go ahead and classify the critical values you got. So classification is the following. Classification of special critical points. If delta at P0 is negative, then P0 is a saddle point. If delta at P0 is 0, nothing can be said yet about the nature of the point. So I make a face, sad face. If delta at P0 is greater than 0, then I have to ramify again. And I get, if A is positive, it's going to look like a smile. Forget about the sad. It's going to look like a smile. So it's going to be a valley point. What do we call that? Relative minimum or valley point. Don't say valley point on the exam, okay? Relative minimum. If A is less than 0 at the point, then locally the surface will look like I have a peak, a relative maximum. Peaks and valleys. Just the way you remember them in Calc 1. Now it's a little bit more complicated because the functions have 2 variables, but some of the patterns can be recognized. Let's go back to our original example. and say, wait a minute, Magdalena, you just gave us a saddle, but we didn't do the whole classification. Yes, we didn't, because I didn't go over the 2 steps. Z equals x squared minus y squared again. We computed the gradient. We computed the partial derivatives. And then what was step 1 in finding the critical points? Solve f sub x equals 0, f sub y equals 0. Solve for x and y. And that's good, because that's going to give me a lot of information. It will give me exactly what the critical points may be. So that is if and only if I need to solve 2x equals 0 minus 2y equals 0. Is this system hard to solve? No, that's exactly why I picked it. Because it's easy to solve. I get the only solution is x0 equals y0 equals 0. So the origin, that's exactly where you put your butt on the saddle when you ride the horse. That is the only critical point you have. The only one. Now, if we want to classify that, what kind of, is it a valley? No. It looks like a valley in the direction of the horse, in the direction of the axis of the horse, because the saddle is going to look like that. This is the horse. That's the head of the horse I'm patting, and this is the tail of the horse. Okay? So, in this direction, the saddle will be shaped like a parabola, like a valley, but in the perpendicular direction, it's going to be shaped going down, like a parabola going down. So it's neither a valley nor a peak. It's a valley in one direction and a peak in another direction. And that's the saddle point. So say it again. What is that? It's looks like a valley in one principal direction and the peak in the other principal direction. And then that's going to be a saddle point. Indeed, how do we figure this out? By the method I provided. Well, who is A? A is f sub x, x at the point. 2x, it was primed one time. F sub x was 2x. F sub y was 2y. F sub xx is 2. F sub xy, b is f sub xy, right? What is that? 0. Good, that makes my life easier. C equals f sub yy. What is that? 2. Okay, this is looking beautiful because I don't have to plug in any values. The D is there for me to see it, and it's going to consist of the determinant having the elements 2, 0, 0, 2. Minus 2. I'm sorry guys, I missed here the minus. And it cost me my life. Here, 2x and minus 2y, and here minus 2.
It didn't cost you your life because you caught it before you were done.
I caught it up. I'm taking the final exam. I still get 100% because I caught it up at the last minute. So 2, 0, 0, minus 2. I knew that I had to get something negative. So I said, for God's sake, I need to get a saddle point. That's why it's the horse and the saddle. So I knew I should get minus 4, negative. All right. So I have, the only thing I have to say as a final answer is, the only critical point of this surface that I'm too lazy to write about, don't write that. Okay. So the only critical point on the surface, z equals x squared minus y squared, will be at the origin O of coordinate 0, 0, 0, where the discriminant being negative indicates it's going to be a saddle point. And that's it, nothing else. You don't need more. But there are more examples because life is hard. And I'm going to give you another example. Well, okay. Suppose we have the surface that's still going to be very easy, but I want to make the first examples easy. I have a reason why. This is a function of two variables, right? It's still a polynomial in two variables of order 2. And how do I solve for the classification of the extrema? I'm looking for local extrema, not absolute. Local extrema. I have no constraint. I'm saying, what do you mean no constraint? Constraint would have been, let's say that x and y are in the unit disk. Or let's say that x and y are on the circle. X squared plus y squared equals 1. That would be a constraint. But they are not constrained about anything. X and y are real numbers. They can take the whole plane as a domain. So I get f sub x equals 0, f sub y equals 0. Solve for x and y. Get the critical values. I get, very nice, 2x. I have to pay attention because now this is not so easy anymore. Plus prime with respect to x, 2y, prime with respect to x, 0, prime with respect to x, plus 3, prime with this, okay, equals 0. F sub y, 0, plus prime with respect to y, 2x, plus prime with respect to y, 2y, plus nothing, prime with respect to y, equals 0. And now you have to be very smart. Well, you have to be perceptive and tell me what I got. What is this telling me? Look at this system. It looks like crazy.
You can set the or can't you just subtract it down?
Is this possible? And what does this mean? What do we call such a system? Inconsistent system. Okay? We call it inconsistent. How can I make this problem to be possible? To have some critical points?
If you add 3,
How about that? Just remove the 3x and see what's going to happen. Oh, in that case, I have something that's overdetermined, right? I have something that tells me the same thing. So I'm priming with respect to x, I get that. I'm priming with respect to y, I get this. I get 0. So I don't need the second equation. And that means the critical point is any point of the form shall I put a Greek letter alpha minus alpha or lambda minus lambda? What shall I do? So any point that is situated on the second bisector. I'm in the xy plane, right? And this is the x and this is the y. And I say, what does it mean x plus y equals 0? Not this line, don't draw it. That is x equals y. The other one, called the second bisector. Y equals negative x. So not this one, that diagonal, but the diagonal that's on the corridor. This one. Okay? All right. So any point of the form alpha minus alpha is the critical point. The question is, how am I going to get to the classification for such points? Can anybody help me? So step 2.
Solve the equation. Solve alpha for one of the two variables first.
Take alpha minus alpha. Could be anything. And then I'll say f sub, this is f sub x, and this is f sub y. What is f sub x? F sub xx, I'm sorry.
That'll be 0.
2.
Oh.
Okay, are you with me? So you know why I'm f sub xy equals 2. F sub yy equals 2. That's the mystery man. The book doesn't give this example and it drives me crazy, and I wanted to give you some bad example where the classification doesn't work, because we always cook up nice examples for you and claim everything is beautiful. Life is not always beautiful. So you get 0. In that case, nothing can be said with this classification. I make a face, sad face. So what do I hope? To get to Maple or MATLAB and be able to draw that. Or a TI-92 if my mother would give me $200. And so I told her. She asked me what to buy for my birthday. I had a TI-83 or something, and it was cheap. I bought it on eBay, and then I stopped using it. And then I saw this TI-92 that can draw surfaces in 3 dimensions. And I said, this is like MATLAB, or you just carry it in your pocket. It's only a little bit too expensive. All right. How about another kind? Look at this. You cannot tell with the naked eye, but you can go ahead and do the step 1, looking for critical values. Solve the system. F sub x will be 6x plus 2y equals 0. F sub y will be, who's going to tell me? 2x plus 2y equals 0. Now, by elimination or by substitution or by anything I want, I subtract the second from the first. What do I get? I get 4x equals 0. And that gives me the only possibility is x0 equals 0. And then I say, okay, if my only one is 0, then y is 0. Right, 0 is 0. So I only have one critical point, which is the origin. Now, do I know what am I going to get? Not unless I'm a genius and I can see 2 steps ahead of the time. I would need to do ABC quickly in my head. Some of you are able, thank God. But some of you, like me, are not. So I have to take a few seconds to see what's going on. A, f sub xx at the point P0. B, f sub xy. C, f sub yy. What do we get?
6.
We get 6. Are we happy about it? We don't know yet to be happy or not.
2.
F sub xy or f sub yx, you see, Mr. Schwartz is now happy that he proved to you that it doesn't matter which order you're taking for a polynomial that's a smooth function. You always have the same thing. And finally, C is 2. And you are ready to do the D. And I could smell that D, but I didn't want to say anything. 6, 2, 2, and 2. Is that a nice thing? Yeah, we haven't encountered this example yet because according to the classification, this is greater than 0. Does it really matter what value it is? No, it only matters that it is positive. And if it's positive, that means I can move on with my life and look at the classification. from this point where delta or D is positive, I'm going to get a ramification into separate cases. And who is going to tell me next what to do? Look at A. Oh, by the way, talking about the quadratic formula from school, from kindergarten, okay? When we computed I'll use the general one, minus B plus minus square root B squared minus 4AC over 2A, okay? We were afraid of some special cases when we were looking at that, especially when delta was negative, those were imaginary and so on. But one thing we remember from 9th grade, was this 9th grade or 8th grade? The parabola opens up when A is positive. Just the same way something opens up when A, big A is positive here, then you have opening up. When big A is negative, then you have opening down. So remember, I'm going to make smile here so you remember, right? So I have it like that. So I suspect that it's going to look like a surface of some sort that maybe is not surface of revolution. You should tell me what it is. You should think about this and do the cross sections with Z constant and tell me what surface that is. But in any case, what do I care? I care that I'm looking at the origin. And this is where my special point is. That's going to be the value point. How do I know? Because A, which is 6, is positive. At this point, I know what I'm left with. I know that my surface is going to look like a valley. So how do I know again? I'm not going to draw it, but it's going to look something like that. At the origin, this is going to be 7. You guys ready? And it's going to open up. And so you should not attempt intersecting with Z equals 5 or Z equals 1, because you're not going to get anything. But if you intersect, for example, with Z equals 9, what you're going to get? If you intersect at Z equals 9, you've got 3x squared plus 2xy plus y squared equals 2. And what is that? It's a rotated form of an ellipse. It's hard to see because it's not in general form, but this is exactly what discriminant is saying. So this is going to be an ellipse. Good. So I know what I'm going to get. What do you have to say on the midterm or on the final about this problem?
The
point is the origin. I classified it. I got delta positive. I got A positive. So it's a value. It's a relative minimum. And that's it. I have a relative mean at the point P of coordinates 0, 0, and 7. And that's the value. Yes, sir.
Why is it A that determines whether it's a relative min or a relative max?
It's a whole story. You can prove it. I don't remember if we proved this in the book or not, but it can be proved. So the fact that it has to do with concavity and convexity. Okay? When you had a second derivative, let's say, what's the equivalent of the calculus 1 notion that you know about? In calculus 1, you had functions of one variable, and life was so easy by then. And f prime positive meant that the function increased, and f prime negative meant that the function decreased. And f double prime was just like your sense that the second partials must have something to do with it, especially the first one with respect to x. If you were in plane and you have f double prime with respect to x, when was this a valley? When you had the smile, when did you have a smile? When f double prime was positive, you have concave up. when f double prime was negative, you can have concave down. Remember, guys? So you have a smile or a frown. This is how it was. For the same reason, that would take about 2 pages to write down the proof. You have a smile for A positive. And the smile means actually in all directions. You have a smile locally around the origin. Okay. Look in the book. I'm not sure how much should we do. Do we give a sketch of a proof or we give the entire proof? But more likely a sketch. Yes.
I asked the slightly wrong question.
Yes.
But I answered it myself. I wanted to ask, why is it dependent on A and not on C?
Not on C.
But then I realized it is dependent on C as well, because if A is positive, then C must be positive.
Yes. Yes, it is dependent on both.
Okay. There we go. That was the question.
So guys, remember, imagine what happens like when you had no B. B would be 0, then the matrix is diagonalizable. And here you have A and C. And Alex says, why would A be more important than B and then C? It's not. But practically, if A is positive and C is negative, that means these are the principal directions in which one bends like a valley up and one bends like a peak down. So this is what happens in the direction of X. F double prime in the direction of X, kind of. And this is in the direction of Y. So this is F double prime in the direction of Y, which we don't denote like that. We call F sub XX and F sub YY, which is A and C. So A positive, A B1 and C being -2 means a valley. Means the valley, means the horse. Look, I'm drawing the tail of the horse. He's a little bit fat, this horse. And that's his mane, his eye. I'm just taking a break. Okay.
It's a pretty good
It
drawing.
looks more like it looks more like a dog or a plush horse or something. So A equals 1 and C equals -2. But if it were diagonalizable, and A would be 1 and C would be 7, both of them positive in any case, then you'd have valley and valley. The X direction valley and Y direction valley. So it has to be a valley everywhere. These are the principal directions that I have. 1 and 2. But then the ultimate case. What happens when A is negative and okay, then either you have them both, one positive, one negative, or you have plus, plus, and minus, minus. Then you have, this is your surface, right? Which one is the X direction? That's the Y direction. That's the second one. The X direction is that. In the X direction, you have a frown. So F sub YY is negative. In the Y direction, you also have a frown. So both of them are negative. So you have a relative max. Yes, sir. Real max. Matthew, tell me.
So isn't it possible to have both A and C positive, but then yet still not be more positive than B squared?
No, because there is a theorem that you.
I was just wondering, like, numbers-wise, like.
You have this matrix, and there is a theorem that shows you that you can actually diagonalize this matrix. You will learn in linear algebra why. When
It makes sense because you're
change the
saying like
base.
A is this way, and that way there's no way you could have 2 cup up and then yet not be a, you know what I'm saying?
Right.
Because then they'd be less than.
Yeah, you
Less than
can
zero.
if you have if you don't have order 2? That's an excellent question. If I would have x to the 4, y to the 4 added together, like a x to the 4 plus b y to the 4 plus something, then I have the so-called monkey saddle. That's so funny. You can have something that looks like that.
Okay.
So in your direction, you can have this. Then I reach 2 equal peaks in the x and the y direction, but in between I also went down. So you can have, depending on a higher degree symmetric polynomial, you can have a monkey saddle. And then it's not just like you can predict what's going to happen in between. In between, if I go valley in the x direction and valley in the y direction, I know that it's going to be a valley everywhere. No. If a polynomial is higher in order, it can go down, valley, and up again, and monkey saddle. It looks like, guys, you have dealt with it when you went to Luna Park or Joyland. Is those one of those things that look like, I'm trying, I cannot draw.
It sounds more like an octopus saddle.
Like an octopus, and one of those things exactly that are shaped so that they are undulated. In some directions are going up, in some directions are going down.
Like an egg carton, almost.
Yeah,
Like, kind of like that.
really undulated. Imagine even a surface made of metal that's undulated and rotating at the same time. They have some of those in Disney World. Have you been to Orlando?
Yeah.
I was there last semester.
But you didn't take me with you, which is bad, because that's one of my favorite places.
I'm just trying to think of what you were talking about so I can visualize
Maybe
it.
we could make a proposal to teach Calculus 3 at Disney World so that we can have examples of motion and surfaces all around and study the motion of all sorts of gadgets, velocity and trajectory. I was thinking last night I couldn't sleep until 1, and I was thinking, I gave examples with sports, winter sports, like bobsled and all sorts of skiing and so on. But I never thought about a skew curve with curvature and torsion that is based on the roller coaster. And the roller coaster is actually the best place to study the Frenet frame. The velocity, the tangent unit, the normal, the binormal, and then when you have in a plane, the roller coaster goes like that, like this and like that, like in a plane, you have nothing but bending, which means curvature. But then when the roller coaster goes away from the plane, you have the torsion. And that makes it sick, really, to the stomach. So we would have to experience that to understand Calculus 3 better. So my next proposal is we ask the administration, instead of a study abroad courses, the domestic study at Disney World for Calc 3. Yeah, it's applied Calculus 3. So, right? Okay, something else that I wanted to do. I had prepared an example. This is an absolute extrema. And you say, what the heck are the absolute extrema? Because she only talked to us about relative maximum and relative minimum, and she never said anything about absolute extrema. And that would be the table, and this will be the extrema. I want to refresh your memory first just a little bit. And this will be the last example because it's actually 2 examples in one. And what if you have, let's say you have f of x equals e to the minus x squared over the interval minus 1, 1. You are in Calc 1, we built a time machine from Disney World, and we went back in time when you actually took Calc 1. And you struggled with this at first, but then you loved it so much that you said, oh, that's my favorite problem on the file. They asked us for two things: relative extrema, mean or max, min-max theory, and they say absolute. But for the absolute, your teacher said, attention, you have to know that how to get to the absolute. You are constrained to be on the segment minus 1, 1. You see, the fact that they introduced this extra constraint and they don't let you move with x on the whole real line is a big headache. Why is that a big headache? If your life would be much easier if it were just e to the negative x squared. Because in that case, you say, okay, f prime of x equals minus 2x e to the minus x squared. Piece of cake, x0 is 0. That's the only critical point. And I want to study what kind of critical point that is. So I have to do f double prime of x. And if I don't know the product rule, I'm in trouble. And I say minus 2 times e to the negative x squared from prime of this and this non-prime plus minus 2x unprime times e to the minus x squared times minus 2x again. So it's a headache. I pull out an e to the minus x squared, and I have 4x squared minus 2. But you say, but wait a minute, Magdalena, I'm not going to compute the inflection points. The inflection points will be x equals plus minus 1 over root 2. I only care about the critical point, and the only critical point I have is at 0. Compute f double prime of 0 to see if it's a smile or a frown. And you do it, and you plug in, and you say e to the 0 is 1, 0 minus 2. So you get a negative. Do you care what it is? No, but you care it's negative. So at 0, so you draw, and you know at 0 you're going to have some sort of a, what? Relative max. Where? At 0, and when you plug 0 you get 1. So you draw a table, and you say relative max at 0, 1. And then you're not done. Because you say, wait a minute, I am to study my function in Calc 1 at minus 1 and 1. It's like you have a continuous picture, and you chop, and take scissors and cut at the extrema. And there you can get additional points where you can get a relative max or relative mean. Absolute max or mean will be the lowest of all the values and the highest of all the values. Okay, so I get at the point minus 1, how shall I put here? X equals minus 1. What do I get for y? And for plus 1, what do I get for y? This is the question. I plug it in, and I get minus 1 over e. And then when I have 1, what do I get? 1 over e again. So do I have a relative mean here? No. No, but I have an absolute something. And what do I have here? Here I have an absolute max. So how do we compute how do we check the absolute maxima and absolute minima? We look for critical points, we get many of them, finally many of them. We compute all the values of z for them, all the function values. And then we look at the endpoints, and we compare all the three values in the end. So in the end, you compare 1 over e to 1 over e to 1, and that's all you can get. So the lowest is 1 over e, the highest is 1. Good. In calculus 3, it's more complicated, but it's not much more complicated. Let's see what's going to happen. You can have a critical point inside. We are just praying we don't have too many. So how do I get to step 1? Critical point means f sub x equals e to the x squared minus y squared times 2x. Alrighty, it looks good. F sub y equals e to the x squared minus y squared times minus y. I'm full of hope because I only have one critical point, thank God. Origin is my only critical point. I don't know what that is going to give me, but it can give me a relative max or relative mean or a saddle. I don't know what's going to be. Who tells me what that is going to be? Well, did I do this further? I did it further. I'm a little bit lazy, but I'm not asking the nature of the point. So for the time being, I only want to see what happens at 0, 0. So I have 1. So in my table, I will put, okay, this is x, y, and this is z. For 0, 0, I'm interested because that's the critical point inside the domain. The domain will be the unit is, and inside at the origin, something interesting happens. I get a 1. And I hope that's going to be my absolute something, but I cannot be sure. Why? There may be other values coming from the boundary. And just like in calculus 1, the only guys that can give you other absolute max or mean, they can come from the boundary, nothing else. Nowhere else in the interior of the disk am I going to look. I'm not interested. I'm only interested in x squared plus y squared equals 1. This is where something can happen. Nothing else interesting in the inside. Just like in calculus. So, to take x squared plus y squared equals 1 into account, I pull y squared, who is married to x. The poor guy is married to x. He is dependent on x completely. Y squared equals 1 minus x squared. And I have to push him back into the function. So at the boundary, f becomes a function of one variable. It becomes f of x only equals e to the x squared minus 1 plus x squared. Are you guys with me? So f of x will become e to the 2x squared minus 1 along the boundary, along the circle. Only here. Okay? Alright, now what else do I need to do? I need to compute the critical values for this function of one variable, just the way I did it in Calc 1. So, f prime of x will give me e to the 2x squared minus 1 times, what comes down from the chain rule? 4x. 4x. So life is hard, but not that hard, because I can get what? I can get only x0 equals 0 here. Okay, so that's a critical point that comes from the boundary. But guys, you have to pay attention when x is 0. How many y's can I have for that 0 on the boundary? This is on the boundary. On the boundary. 2 of them. I can have 1 or I can have -1. There is one more tricky thing. This is a function of one variable only, but this thinking function is not defined for arbitrary x real. So I make a face again. So I go, oh, hit it. Why? X is constrained. X is constrained. You see, if you are on the inside the disk, x must be between -1 and 1. So I have to take into account that x is not any real number, but x is between -1 and 1. Those are endpoints for this function, and in Calc 1 I learned, okay, I have to also evaluate what happens at those endpoints. But thank God that will exhaust my list, so I have a list. -1 for x and 1 for x, thank God that will give you what? Y on the boundary. When x is 1 and x is -1, you are interested in what happens, maximization or minimization for this function at the endpoints. But fortunately, since you are on the boundary, y must be 0. Because that's how you got y out. If x is plus minus 1 on the boundary, y must be 0. So my list contains how many interesting points? 1, 2, 3, 4, 5. For all of them we need to compute and we are done. Of all of them, the lowest z is called absolute minimum, and the highest z is the absolute maximum, and we are done. You guys need to help me because I'm running out of gas. So, x is 0, y is 1. What is z? E to the -1, you were fast, 1 over e. Thank you guys. So when x is 0 and y is -1. Huh? No, it's the same. Because x is 0, y is -1, I get e to the -1, which is 1 over e. So far, so good. I'm circling all the guys that I want to compare before, after. So, for the final 4 points there, what do I have? My final candidates could be x equals plus minus 1 and y equals 0. E and E. Who's the biggest, who's the smallest?
E is the biggest.
E is the biggest and 1 over E is the smallest. So how do I write conclusion? Conclusion. We have 2 absolute maxima at -1, 0 and 1, 0. And we have 2 absolute minima at 0, -1 and 0, 1. Okay, now I have to, now that's like a saddle that, okay. Can you see it with the eyes of your imagination? It's hard to see it. This is the disk, and the 4 points, the cardinal points, okay. This is the disk. We are looking at this disk from perspective. And the 4 points, the 5 points, 1 is in the middle, okay? 1 is here, -1, 0, 1 is here, 1, 0, 1 is here, 0, -1, and 1 here, 0, 1. At -1, 0, and 1, 0, I get the maximum. So the way it's going to be shaped would be like that. In this direction will be like that, and cut the cake here. You see, it's like that. It's going to be like this. Okay. I'm passing through the origin. With my hands, I'm molding the surface made of Play-Doh or something for you. So I'm starting here, and I'm going up. And at those points, I'm here. Are you with me? The same height. In the other direction, I'm going from 0, but I'm not going so high. I'm going only up to, what is 1 over E? About 1 over 3, something like that. So I'm gonna get here. So the problem is that 1 will be in between. So if you really want to see what it looks like, we are here at 1. We grow from 1, altitude 1. You see? We grow from 1 to about 2.717823 for both of these. And from 1, in this direction I have to go down to 1 over e. So it looks like that. I'll try to draw, okay? No, not very good. Do you see the patch around the origin? So here's E, and here's 1 over E, above the sea level, and this is 1. And you have one just like that in the back. That is it still looks like a saddle. It is a saddle, symmetric, but it's another kind of saddle. There are all sorts of saddles made in Texas, different ranches, different saddles, okay? So, that was the harder one. The ones that I actually saw in the finals, and the last 3 or 4 finals were much easier, in the sense that the table you had to draw was much shorter than this one. Okay, in principle, 1 critical value and 1 max and 1 mean point. But you have to be prepared more, rehearse more, so when you see the problem in the midterm, say, oh, that is easier than I'm used to. Right? That's the idea. Okay, go home, send me emails by web work. We still have time to talk about the homework if you get stuck. And I'll see you Thursday.
I was thinking of 5, but still.